Yeah, so it's 3:10, and now they're starting slowly. I guess we got the
Walczak is going to tell us about something hot, something red. Prescribing mean curvatures of foliations. Thank you.
Thank you very much. Thank you, Gael. Okay, so I will start with mathematics, and other comments will be at the very end. At the end. So the title is Prescribing Mean Curvatures for Foliations. You can read this, probably if you can read, because on the screen of the computer it's much better than here. Okay, but anyway, then you have Latin, Portuguese, and Polish version. I can read Polish version, probably for you. So this is wyznaczanie średniej krzywizny foliacji. Okay. So I think that Paul understands all these languages, including the second one from the top, which is supposed to be Latin. Okay. So probably this is enough about the first page, the first slide. So the setting is more or less the following, that we have a foliation of a closed manifold of given dimension, everything oriented, therefore foliation is oriented and transversely oriented at the same time. By Riem of something, we denote the space of all the remaining structures. Then given G, a remaining structure, we denote by either small h or capital H, the mean curvature function or vector. Mean curvature vector is defined in any codimension. Mean curvature function is defined only in codimension 1. So this mean of f is the space of all the mean curvatures of f with respect to all the remaining structures on our manifold M. And the problems to be considered are decide when f is geometrically taught. That this means when the constant function 0 belongs to our family mean of f. So in other way, when can we find the remaining structure such that all the leaves become minimal? And the second problem is describe the space as much as we can, the space mean of f of all mean curvature functions when codimension is 1, or mean curvature vectors for arbitrary codimension. Well, describe as much as we can. So the problem, the first problem was originated, I think, by Dennis Sullivan and Hans Klaus Rummler. In fact, the paper, Rummler's paper, was the first paper about foliations I read. Because it happened that in 1976, in 1976, this paper didn't exist, but probably the preprint existed already. I visited Helsinki, and I tried to tell these people that I have an idea of describing mean curvature functions for distributions which are integrable and so on and so on. At that time, I didn't know the term foliation. And they told me, do you know the term foliation? I said, no. Oh, so maybe you should read a book about that. And they mentioned also Rummler's paper. So this was the very beginning of my relation with foliations, not with Paul, but with foliations. Okay, so let me recall that the mean curvature vector is defined as the trace of the second fundamental form, here of the leaves. If codimension is 1 and f is transversely oriented as it is in this story, then we take the unit, positively oriented unit normal, and we take the inner product of the mean curvature vector with this n, capital N, and we get a function which is called mean curvature function. So they play mean curvature in general plays very important role in differential geometry. The story of minimal surfaces in R3 is, I think, more than 300 or more than 300 years old, and is very well developed. And this is one of the very important notions. Okay, so mean curvature, in fact, plays the role of the derivative of the volume. Maybe I should say the gradient for the volume. Volume form of submanifolds here of the leaves. So we have the volume form omega vol f, volume form of the leaves defined by the Riemannian structure, and then the formula, which is called Rumler, but as far as I know, it appeared also in some papers by Brito, Langevin, and Rosenberg, something very similar. I think so. Maybe Remy knows better. Shows that the differential of the volume form is somehow closely related to the mean curvature vector. So this formula was used by Rumler to prove his main result in this paper. The main result says the following. If you have a foliation with all the leaves compact, then it's geometrically taught in the sense of this definition here at the bottom, if and only if the space of the leaves is Hausdorff. This is equivalent to saying that the volumes of the leaves are bounded. Well, our manifold, in general, it's equivalent to a local bound for the volume of the leaves, but since our manifold is compact, local bounds implies global bound. So, and also to the following property, holonomic groups of all these leaves are finite. So this shows that the geometric property of being geometrically taught is somehow closely related to some topological properties of the foliation. Foliations with all the leaves compact may admit in codimension bigger than 2, I think, admit so-called bed set, that is the set of all the points such that the volume form in the neighborhood of this point is never bounded. So this is more or less the content of this paper. Okay, now to describe, now I am going to concentrate on this problem of number 1 of geometrical tautness. Dennis Sullivan used Schwarz distributions to describe, to somehow to find some equivalent conditions for geometrical tautness. So P currents are members of the space D sub P dual to the other P, dual to the space of differentiable P forms. And now, given a closed subset of M, you may take just A equal M. We can consider, well, we will consider the following subsets. CF, which is the closed convex cone generated by all the Dirac currents of the form E1 wedge EK, where E1 to EK is a positively oriented frame of the tangent space of the space tangent to our foliation. This vector like the K vector like that could be is considered as K current operating on forms in the following way. E1 EK on omega is just omega on the vectors E1 to EK. And then we also consider the closed linear subspace generated by the boundaries, or, well, okay, so the exterior derivative differential in the space of form induces the dual boundary operation in the space of currents. So this dual stuff is denoted by D asterisk, D star. And so we consider all the boundaries of the form also generated by k+1 vectors, such that one is arbitrary, V is arbitrary, and the other one are as above. Okay, so the first stuff is a cone, closed convex cone. The second stuff is closed linear subspace. Both of them live in the space of all the k currents, which is huge. They are also huge. So definition is the following, that foliation is homologically taught when these two objects, this linear subspace B and the cone C, intersects only at the origin. So maybe I draw a simple picture. If I can find a tool. Yeah, there is something here. Okay. No, maybe. This is not that easy. So the picture is really extremely simple. So we have this hyperplane B. This is the origin. You have a cone, which is called CF. This was called BF also. And what is important is that the cone has compact base. And therefore, it follows that, let's say, base, I don't know, I should use the letter B, but I cannot. C0. Then this means that there exists a linear functional which belongs now to the space dual to this one, dual to the space of k currents. My notation is maybe not the best one, but the dimension of the foliation is k. But this is known to be isomorphic to the space of k forms. So this means that there exists lambda such that lambda on the space B vanishes identically and is positive, strictly positive, or maybe equal even 1, is constant equal 1. Okay, on the base. Okay, so this is what I wanted to show briefly as a picture. Now I should come back carefully. Down. So now, the following theorem is known due to Dennis Sullivan, that geometrical tautness is equivalent to homological, or some people say topological tautness. So one implication follows directly from the Stokes theorem and maybe just from the Stokes theorem. And the other one is more complicated. It uses first compactness of the cone, existence of this compact base. Banach theorem, which allows to extend some linear functionals, or maybe even not linear, but let's say in particular linear functionals defined partially to the whole space. And then what is important is also this fact, the fact is not listed here, this one that the dual space, the space dual to currents is the space of k forms. And also the procedure of so-called purification of differential forms, which was described by Sullivan in this paper, and I think in this one. Yeah, I think. And what is important is that this purification can be done for arbitrary distribution by the fact that the distribution, I mean the tangent bundle of the foliation is involutive or integrable, if you like, implies the following fact, that if you have, if h is 0, right? If h is 0, then my form omega, the volume form, is closed when restricted to vector fields of vectors of this form. One arbitrary and the other one's tangent to the foliation. So if this d omega vanishes on all the vectors, all the k plus 1 vectors of this form, we say that it is F closed. So the integrability of the tangent bundle to F implies the following, that purification of on an F closed form is F closed, as far as I remember. So anyway, this is the sketch of the proof of the Sullivan's theorem. Now, when we restrict to codimension 1, it's quite easy, or easy, it's not easy. It's again the Sullivan description of tautness. Codimension 1 foliation is taught if and only if every compact leaf is cut by a closed transversal curve. This is, in fact, equivalent to say if and only if every leaf intersects a closed transversal. And in particular, this implies something what is written at the bottom. A codimension 1 foliation is taught if and only if M contains no positive or negative domains. A saturated domain, saturated by leaves, is said to be positive, respectively negative, whenever the positive-oriented vector field N points either outwards or inwards along the whole boundary of D. So in particular, if the boundary consists of one leaf, like a rep component, then it is of one of these sorts, either positive or negative. So in particular, taut foliations admit no rep components. Or more general, more probably generalized rep components neither. Okay, so then in codimension 1, we can prove that, well, some of these results are due to me at the very beginning of my interest in foliation theory, but in fact, the person who got this result is a Japanese mathematician, Oshikiri. So he described very nicely the space of all the functions which can become mean curvatures of a foliation, of a given foliation. So if F is taut, then a function, if capital F is taut, then a function small f belongs to the space of mean curvature functions, if and only if it's either identically 0, what follows from Sullivan's results, or is positive somewhere and negative somewhere. So there exist points x and y such that the product f of x, f of y is negative. This is the only obstruction. The obstruction comes from the fact that the integral of the mean curvature function over a closed foliated manifold is always equal to 0. Therefore, the integrand cannot be non-negative everywhere, non-positive everywhere, except of the case equal identically to 0. So if f is not taut, it contains these positive and negative domains, then the function f becomes mean curvature for some Riemannian metric, if and only if it is positive or negative at some points of any positive or negative domain. So I think this is a very nice result, showing that in fact these abstractions are very, very weak. Just proper sign and some particular points. Okay. Now we are coming to results obtained by two Poles, Paul Schweitzer and Paweł is also Pole in Polish, okay, so we are Poles. In a paper published, I don't know, in 2004, I think. Is it written something here? No. Not yet. Okay. So to do that, so now we want to consider the similar problem as it was before, just for codimension bigger than 1. Then we cannot speak about mean curvature functions, but we could speak about mean curvature vectors. So the question is that if we have a smooth vector field on M, is there any chance that X becomes mean curvature vector of a given foliation? So notation is like that capital sigma denotes the set of all zeros of X, and for given closed subset of M contained in the complement of sigma, we consider subsets of sets of currents determined by both F and X. And one of them is closed cone generated by all the boundaries of the form. Oh, now I used this D instead of D star. Okay, but this strange D is the same as denotes the same as D star. So we take or positively oriented frame of the tangent space to the foliation, and we multiply this, we take the wedge product with capital X at the same point. Always negative sign, but this is just a matter of convention. Now, so this is one cone. The other one is, okay. Before I defined the cone, which was, this one, just CF. Now we restrict the points we restrict ourselves to this given set I. And now, so we have two cones, CF, this is, okay. We have CF and CFX, CFX tilde. So now we take the union of these two things, and we generate the new cone, closed convex cone, generated by the union of the two. And also what we need is another closed linear space, which is also related to our field X, vector field capital X, vector field X, which is generated by all the Dirac currents of the form X of X, which a suitable number of, should be K here, vectors tangent to the foliation. So situation is a bit more complicated. We have another cone which is called CFH, right? CFX tilde. So now we have two cones. This one has compact base, but unfortunately there exists vector fields X such that this cone has, so may do not admit, or has maybe have a compact base. And now using these two cones, we generate a new one. So you can imagine probably without the drawing. Then we do something like that. That we take the union, just the union of these two cones, and then the convex hull of this of the union. So since this cone may not have no compact base, then the union of these two has the same property. Okay, and there is another closed linear space which is not in the picture, but okay. There is another closed linear subspace, space of currents. And now, okay, so first, okay, so like somehow back to almost to the very beginning, the cone CF has a compact base. That is, there exists a continuous linear functional, like I wrote here, positive on the complement of 0, of course, and such that the inverse image of 1 intersected with this cone is compact in the space of all the currents, which have some topology. Obviously, since this holds for the whole M, then it holds for closed subsets of M. But this argument cannot be applied to the cones, which these cones depending on X. The picture, for example, this is not a picture. Oh no, okay. So this is a kind of example that if you take a closed-oriented 3D manifold equipped with a two-dimensional foliation and a nowhere vanishing vector field X transverse to F, if our foliation contains a rep component bounded by a two-dimensional torus, then both currents, integration over T with two different orientations, belong to the cone C tilde Fx. But one is, both of them are boundaries of the integrals over either rep component or the complement of the rep component. And these integrals can be expressed as limits of convex combination of direct currents of the form we want. Therefore, the cones with tilde and without tilde, these cones CFX, contain two non-trivial elements, plus and minus C. C is probably the integral over T. So a cone like that cannot have compact base. The same argument applies to codimension 1 foliations, which admit positive or negative domains in the sense I described before. Okay, but now in our joint paper with Paul, we proved that if X is the mean curvature, then the cone CFX, the one generated by the red and blue one, by the union of the red and blue one, has a compact base. So this is a kind of condition necessary for X to become mean curvature. And in fact, the volume form of the leaves satisfies the required condition after some maybe normalization or things like that. So anyway, okay. Now, if the theorem, one of the main theorems in this paper is the following: that if we suppose that if we have a Riemannian metric on a neighborhood U of this singular set sigma, such that X is equal to H0 whenever it defined, I mean on U, and we can find a smooth compact submanifold of M such that it bounds in somehow surrounds is a neighborhood. I know. Okay. Okay. This is the compact submanifold with boundary such that the interior contains the singular set and the manifold itself is contained in this neighborhood U. And A is denotes just the closure of M minus B, so they have the common boundary. Then a Riemannian metric on M extending G0 and such that X is equal to H everywhere on M exists if and only if the cone has a compact base, as in the proposition before, and intersects the space P, which is slightly different from this one, but again, this is some linear subspace, intersects this space trivially. So all these results show, I think, that the realization of either a function or a vector field as mean curvature is a kind of topological problem, not really geometric, but topological. So here we have a picture showing that okay, so in particular, a nowhere vanishing vector field on a closed foliated manifold can become the mean curvature if and only if the cone under consideration has a compact base and intersects the space trivially. So this is slightly maybe simpler statement than the one in the previous theorem. Now here we can see that we can see a vector field which cannot become a mean curvature. In fact, this comes from the fact that mean curvature vector field up to with the suitable sign plays the role of gradient of the volume on the leaves. So if you have the situation like that a small domain is mapped by the flow of the vector field X to a larger domain containing the small one inside, then something like that cannot happen for mean curvature. But of course, situations like that exist. I mean, vector fields satisfying something like that do exist. At what time did they start?
At 10. I guess you still have 15 minutes.
15, okay. So this, what was said, what I told you before was realization of a vector field as a mean curvature far from singularities. Now, is it anything we can do around singularities? So there is a little, I think. I think this is not satisfactory for the authors. That if by chance my vector field X takes values in a subbundle, regular subbundle, I mean, subbundle of the tangent bundle, complementary to the tangent bundle of the foliation, and well, this bundle E and the set of singular points satisfy some condition where new spaces of currents appear, unfortunately. The space, the CF is the cone which was defined before. Now the question is, okay, at the very bottom here you can see that here PFE is the closed, again the closed subspace of currents generated by all the Dirac currents of the special form, when now W is an element of the fiber of my bundle E, and VIs are tangent to F. So this is another subspace, space of currents to be considered. But anyway, the result is more or less like that, that if X is a gradient field, I mean gradient of a function, some open neighborhood U of this singular set, and the cone generated by the red and blue one has a compact base and intersects this subspace P trivially for any closed set contained in the complement of sigma, then there exists a Riemannian metric for which X becomes the mean curvature. Oh, probably, no, maybe it's okay. Okay. So I think that still a kind of open problem is improve our results. So you are welcome. If somebody has an idea, then it would be very nice. Okay, now coming back to codimension 1 case, Oshikiri, the Japanese mathematician mentioned before, proved the following, that if you have any vector field Z transverse to a codimension 1 foliation of a closed-oriented manifold, then there exists a smooth function supported supported all over M. This means that, well, the set of zeros of this function is rather small, such that the product of this given function, of this given vector field Z with F becomes the mean curvature for some Riemannian metric. So this was proved, this was published in Illinois in 2005. Most of what I have told you today is contained in chapter number 3 of the book I wrote together with my Israeli colleagues Vladimir Rovensky in a book entitled Extrinsic Geometry of Foliations, which was published last year. Okay, so maybe so this is the last slide devoted to mathematics, and now there will be 2 more. So the first one shows up to some mistakes and some mistakes made by myself, produced by myself. The history of our relation of the 2 poles, right? So the first we met at ICM in Warsaw, but ICM 82 was postponed to 83, so this was the first. So we met for the first time in 83. Then in 86 I was invited to Brazil for several months, to São Paulo, but I came to Rio once or twice, probably twice. And then we met, of course. Then the list is very, very long. Several times at ICS. Well, of course, the list is totally not complete. So, for instance, I am sure that the list of countries even is not complete. We met definitely in Spain and probably in Germany also during the ICM of 1998 or something like that. No. Okay, so anyway, nothing is complete here. And moreover, this list is equipped with some letters which denote members of my family. P, of course, stays for me. Z, Z for her. And B, S, and M for our children, because at some moments we used to meet Paul in some, or all the family, of a part of the family, etc. In fact, this slide is especially devoted to Paul, not to all of you. No? So finally, I would say all the best for another 85 and a quarter, because Paul was born in July, that's true. So 3 months ago, the birthday, the real birthday was in July, and now we are maybe 3 months and a half after, but okay, let's say that 3 years, 3 months, this means 1/4 of a year. From me, all the family, this W stays for Walczaks, and the colleagues from my department, which is called Katedra Geometrii Uniwersytetu Łódzkiego. Okay, so this is all what I would like to say using the slides. But since this is the last lecture of this conference, I would like to express first my personal thanks for inviting me to Brazil, to this conference, to this wonderful conference. And then I think I should also express the feelings of all, or at least most of, the participants, saying that we express our best thanks to the organizers who are somewhere here. At least I know some names, but not all, because probably there are some people who didn't send mail. So anyway, Paolo, Emilia, Slobodan is somewhere. Oh, okay. And everybody else about whom I don't know. So our best thanks to all of you. In fact, the conference was wonderful. I think there was a number of good lectures, forget this one. But in fact, some of them were really, really exciting. Thank you very much.
Well, are there questions to Paweł?
Looking back on this work we did years ago and hearing your clear exposition, I wonder whether in the case of singularities, you could suppose that in the neighborhood of the singularity, there was a Riemannian metric making it the mean curvature, making the given vector field a mean curvature, and perhaps work away from that. What do you think?
So I think that it may happen that the metric like that exists or not, because it depends on the structure of this set, no? I don't know. Oh, it's possible that, okay. This means that some of the leaves should be, at some points should be minimal. No, this is really not so easy, I think. Maybe I didn't understand the question.
No, I'm thinking you have conditions for a non-singular vector field to be realizable as mean curvature. So I'm suggesting that you have small neighborhoods of the singular set on which you can realize it and try to combine that with conditions on the complement.
No, so somehow it was in this theorem, right? That if we have a metric G0 in a neighborhood of the singular set, that we can, under some conditions, we can. It's like that. The theorem says more or less the following: if we can realize our vector field X as mean curvature in a neighborhood of the open of the singular set, then for this particular metric can be extended to the whole manifold. Maybe it's like that. You restrict a bit the domain, then you extend to the whole manifold, providing X to be mean curvature everywhere. I think this was the statement of the theorem.
I didn't understand that. You had sigma and E, but I didn't see that anywhere you had a mean curvature vector near sigma.
So, oh no, I changed some. No, okay. Suppose that G0 is a Riemann metric on a neighborhood of sigma, right? And then you just take a smaller neighborhood, but more regular, and then from this smaller regular neighborhood, you can extend the metric to the whole M. More or less like that.
More questions? No more questions, including online?
Can I ask some?
Please.
Do you hear me?
Yes, very well.
I see. So this is Yoshi. So I have a quite general question. So for the tautness criterion, in codimension 1 case, it's really nice. So we have equivalent conditions, but for higher codimension case, so basically we have only one.
Oh, I'm afraid that for codimension bigger than 1, we have no conditions like in codimension 1, unfortunately. And I think that we spent some time discussing with Paul, but we didn't get anything geometric or geometric like in codimension 1, unfortunately. In fact, I think that in the whole theory of foliations, it's like that foliations of codimension 1 are known much better than foliations of codimension higher than 1.
I see. So I asked because long ago I formulated a tabulation of two-dimensional foliation on four manifold, but in that case, unlike in the codimension 1 case, once you tabulate the foliation, then it becomes tighter, more taut, if you use a criterion or in the Sullivan's fashion. So I'm looking for quite slightly different formulation of tautness. So it's always embarrassing.
No, what do you mean by either formulation of tautness in codimension? In codimension 1, I think it's okay, right?
No, codimension 2 or 3.
2 or 3. Oh, okay. Okay, maybe one day. Hopefully, let us hope.
Thank you. And thank you for the nice lecture.
More questions? So this is the end of the last talk of this wonderful feast in the honor of Paul's birthday, and just as Paweł just said, the organization made it very nice also. So let us thank, well, may I be very naive, let us thank Paul for being here with us and all this, because I feel that there are a few people in this subject who really make the subject socially in the same time as scientifically are able to make the subject live. And Paul is one of these very few. So let us thank Paul for everything that he did up to now and the organizers of this conference.